Bismillahirrahmanirrahim. Today we'll talk about capacity of additive white Gaussian noise channels. This is lecture number 34, week number 14. So in this lecture we'll talk about the fundamental limits on the performance of communication systems. These limits were first introduced by Claude Shannon, 1948, which is called information theory now. So he introduced the mathematical theory which gave the fundamental limits of the performance of communication systems, that how much information can be sent across various channels, and specifically talked about additive white Gaussian noise channel. So what are the fundamental limits or the fundamental measure of performance that can be achieved for a communication channel? So that phenomena or that fundamental measure for a given communication channel is called capacity. So what is the definition of capacity? Capacity means that the maximum amount of information or the maximum amount of rate of communication for which at the receiver side we have very small probability of error that can be achieved. So in wireless communication systems we are interested in fading channels. So we will talk, or we will try to find out the fundamental limits or the maximum amount of information that can be transferred over flat fading and frequency selective fading for point-to-point communication. That would be our ultimate goal. But first we have to go through the fundamental limits defined by Claude Shannon for additive white Gaussian channels. Now the results for these channels are developed, results of flat fading and frequency selective fading channels for point-to-point communication systems can be derived from the already established theory of information transfer for AWGN channels and time invariant ISI channels. So first we have to review the capacity of the AWGN channel. So for that we will talk about discrete time real AWGN channel. So this is a equation for the input-output model for AWGN channel in discrete time. Ym is equal to xm plus Wm. AWGN channel means that Wm is a normal distribution with mean zero and power or variance sigma square. Now we have to assume that from the transmitter side the power transmitted on the symbols is smaller or equal to P, and that power transmitted is basically the average transmit power across all the symbols. That should not be greater than P, it should be smaller than P or equal to P at least. So what Claude Shannon defined is that capacity, or the fundamental limit or the fundamental amount of information that can be transferred on AWGN channel, is given by half of log of 2 into log of 2 of 1 plus P over sigma square bits per transmission. So that is the amount of information you can send, or the amount of bits that you can send per channel use or per transmission without significant number of errors at the receiver. So for details of trying to find this equation, you can see section 5.1.2 and appendix B.5, in which an heuristic argument is given based on Package spheres. So this section 5.1.2 and appendix B.5 is from the book Fundamentals of Wireless Communication from David Say and Vishwanath. Now, rigorous proof of this information theoretic aspect of capacity can be found out in many classical books. And in fact, from the Claude Shannon basic paper, the proof is basically the two types of proof. One is achievability proof, that for R is smaller than C, that how much rate can be achieved which is smaller or equal to the capacity, and converged theoretical proof is also given in those books, in which you need to find out the amount of rate that is greater than C. So information theory gives you an idea about how much data rate, maximum data rate you can have. So that maximum data rate is basically the capacity. So the practical codes that achieve performance close to capacity have been also constructed for this AWGN channel. So you can perform some kind of channel coding on simple blocks of data that you are sending to achieve capacity or increase the amount of information that you can send with a lot of with very less errors. So with channel coding, you can basically decrease the probability of error. So when you decrease the probability of error, it means that you can send more information which is reliable. So example, if you have a signal to noise ratio of P over sigma is equal to 1, 0 dB, and for that case you have capacity equal to 1 over 2 bits per transmission. So this means that if power of the transmitted signal and the noise variance power, they are the same, or the ratio is equal to 1, so that means that at the maximum, the capacity in AWGN channel is half bits per transmission. So to send 1 bit, you have to use the channel 2 times. So LDPC codes, which are linear dispersion parity check codes, with a block length of 8000, can get BER of 10 to the power minus 4 at 0.1 dB. So you can see that the BER is very less, and the SNR can be achieved, it is equal to 0.1 dB. So lower BR can be achieved at 0 to 0.1 dB by increasing the block length. If we increase the block length, we can get the BER at less than 0.1 dB. Or we can say in other words that 10 raised to the power minus 4 can be achieved at less than 0.1 dB by increasing the block length. So if we increase the block length, we can get BER 10 to the power minus 4 dB at even lesser power than 0.1 dB. So one aspect is that we have to increase the block length. So over n uses of the channel, if we use the channel n times, so we need to send 1 of 2 to the power n into r messages to achieve this rate r. So that is the basic idea of the capacity. So now we will study about the continuous time AWGN channel. So we know that the channel is normally band pass with a bandwidth of W hertz. This is the transmission bandwidth, and assume that the transmit power constraint. So we transmit symbols with this power constraint P dash at this bandwidth W hertz. So AWGN channel with power spectral density is given by N naught over 2. So if we convert this passband channel to baseband conversion and do the sampling at W complex samples per second, we get complex discrete time AWGN channel. It means that you can convert your continuous time AWGN channel to complex discrete time AWGN channel, which we already decided. So this can give you a relation between the discrete time channel and the continuous time AWGN channel. So discrete time AWGN channel is given by Ym is equal to Xm plus Wm with these information as given before, but instead of sigma square now we have N naught, which is noise spectral density, single-sided noise spectral density. So means that it is IID, identically independently distributed. Wm is circularly symmetric. So that is why Wm here is now Cn, complex normal distribution, which means 0 n spectral density or spectral power is N naught. So now the transmit power constraint per sample, because these are the samples, W samples per second. So that would be given by P dash into 1 over W. So complex samples contains 2 real channels. So AWGN discrete time would be having the power, and the sigma square would be equal to N naught over 2, and P would be equal to P over 2W, because there are 2 real channels over W. So if we multiply this thing by 1 over 2, we will get P dash over 2W. So power constraint is now not simple P, it's equal to P dash divided by 2W. So if we put the values in the main equation that was given before, log of 2 into 1 plus sigma square. So instead of SNR, we have to put P dash divided by N naught over W, bits per complex sample. So this equation is different from the previous one for the continuous time case. So for the discrete time case, so it's this equation is equivalent of the continuous time AWGN case. So C of AWGN P dash comma W, it would be equal to W log of 1 plus P dash over N naught W bits per second or mega samples per second. Or we can also write this as C of AWGN is equal to log of 1 plus P dash over N naught W, which is basically defined as SNR or bits per second per hertz. This is called the spectral efficiency. So now we will see the effect of the power and the bandwidth on the change in the capacity of the system. For this, let's suppose that W is fixed now. So as we increase this power, C increases, as evident from this equation. But how does it increase? Does it increase linearly, logarithmically, or what? So for small p by P dash by N dot W in this equation, C is approximately equal to W into P dash divided by N dot W log 2 of E bits per second, because log of 1 plus X is approximately equal to X for small x. So the capacity increases linearly with P because C is proportional to W into P dash divided by N dot W. So the capacity increases linearly with P. So if P doubles, capacity doubles. Now for large signal to noise ratio, P dash over N naught W, C is approximately equal to W log of T P dash over N naught W bits per second, because log of 1 plus S is approximately equal to log of X for large X. So the capacity increases logarithmically with P. So if P doubles, capacity increases by 1 bits per second per hertz, or W bits per second. So it is a concave function. Concave function means diminishing returns. Now suppose that the P is fixed. So what happens if we increase W? How does the capacity equation change with increasing or decreasing W? So when we increase W, the number of degrees of freedom it increases, and SNR per degree of freedom decreases. So C is an increasing function of W. So for small W, SNR per degrees of freedom is high. Increasing W rapidly increases C, since the increase in degrees of freedom is more than which compensates for the decrease in SNR per degree of freedom. For large W, SNR per degrees of freedom is low. So increasing W or bandwidth has a very small impact on C, since the reduction in SNR plus degrees of freedom also decreases C significantly. So this equation, W log of 1 plus P log of 2 of 1 plus P dash divided by N naught W is approximately equal to W into P dash log 2 of P divided by N naught W, which is approximately equal to P dash divided by N naught log 2 of P, because W cancels, as log of 1 plus X is equal to X for small x, because when W is large, this thing is very small. So this is called the power limited region. Now C depends mainly on P dash. So when we increase P, the capacity increases at this large W. So that is why it is called power limited region. So as this omega or W goes to infinity, C of omega goes to P dash over N naught into log 2 of E bits per second. So this is given in this equation. So that is the limit. P dash over N naught log 2 of E goes like this. So this is the power limited region. The region is limited by the power. Even if the bandwidth is not constrained, the capacity of the AWGN channel with limited power is finite. So at a given point or given power level P, minimum required EB, that is called the energy per bit, is equal to P dash over C AWGN P dash W. So P dash divided by, if we put the equation values of this equation here, we get this value. So the minimum EB by N naught can be given by this equation. So as P dash goes to 0, we have EB by N naught minimum, that is 1 over log 2 of E, it is equal to minus 1.59 dB. So EB by N naught minimum will be higher in the finite bandwidth region. So this is this value is basically infinite bandwidth. Now to achieve this minimum minus 1.59 dB, that is energy efficiency for a fixed W rate, data rate in bits per second goes to 0 and delay increases. So that means that energy is spread over long time interval for infinite W. Power is spread over large bandwidth. So orthogonal codes, they achieve capacity in the infinite bandwidth. So that is for this lecture.